So the meeting will be recorded, guys. So again, if we look at this column example, so we can use it to go through the beam design procedure and the column design procedure as well. Okay, so if, for example, this B1 was similar to what you have done in project part A or part 1. So for project part B, we need to design beam B2 and column C3 or C1 in your project, right? So this is the main pieces of report or project. The idea or the difference between beam B1 and B2 and C3 is B1 is a part of the roof, right? And B2 is a part of floor. So the beam supporting a floor is different from the beam supporting a roof. Okay, so B2 and C3 are the supporting floor. So all the dead loads and live loads for floor are different from the live load and dead load for roof. Okay, so if we look at this example here, for the dead loads, what was the flooring? Because this information is not given to you in the project, so you need to make a search and find it. So you can use steel grating as the flooring system for this mezzanine floor. Okay, so this floor cannot be like roof sheeting. This is not correct. And insulation and purlins and so on, what you have done in stage 1. Okay, so this flooring should be any material you think it is good for flooring, but if you need an example or a guide to use, this example is good for you. So you will have the flooring as a 505 by 2 steel grating. The on weight of this one is 51.5, and we will be using some secondary beams. So these are the secondary beams here. Okay, and the main rafter or B2 will be 530 UB 92.4 and no walls or partitions. Okay, and for live load, this floor will be used for storage, right? Do you have you seen this information? Yes, we should assume the number of secondary beams based on what you have in your project. So, for example, if we look here, how much is this distance? 10 meter, right? So you can have, if the spacing between the secondary beams is 1, so you will have almost 10 secondary beams. Okay, if it is 5, so you can use like 5 secondary beams. So the number of secondary beams would be assumed. Okay, up to here is okay. So do you understand why the flooring should be different? Because B2 is supporting a floor, not a roof. Okay, so I will just add another slide here because this part is not included in this example for the beam design, the steps for beam design. Okay, so again for dead load, we assume steel grating. The self weight of this one is equal to 51.5 kilogram per square meter. The secondary beams are 310 UB 40.4, this for example. So if we look at the plan, your plan in the project, if this is P2 and this is the columns, and this is a column. So the secondary beams will be running in the other direction or the perpendicular direction, like that. So we'll have one secondary beam, one secondary beam. Whatever the number of secondary beam is, you can assume it whatever the value you want. So for example, if you assume it in this similar to this example as 1.1 meter between each of them. So this blue are the secondary beams. Okay, and the third assumption we have here is our main beam or our main rafter for B2 is 530 UB 92.4. So all these three information are assumption or assume these three values. So you can assume these three values to start your beam design, beam 2 design. Okay. So there is no insulation here or ceiling or purlins. So just steel grating or flooring material, secondary beams and main beam. So if I ask you how much W or dead load on B2, the dead load on B2 will be, sorry, we can call it G instead of W. So G will be G of the flooring plus G of the secondary beams plus G of the self weight of the rafter. So G on rafter or dead load on the rafter will be this three component. Okay, so we have one, two, three component. Okay.
Sorry to interrupt. Would we also need services on there too?
No.
No? Okay.
Yeah. Just try to follow this example. This will be the easiest way. Because
Okay.
you know this is a mezzanine floor, so it doesn't have a lot of notice the floor in the middle just for storage, so it doesn't have many things. Just
Okay.
to need the strong material to, because as you know the roof sheeting is very thin and it cannot carry much load, right? So just need to use this type of flooring to be strong enough to carry some loads.
Okay. Thank you.
No worries. So if we now sorry. So if we now want to start the calculation, how much G flooring? How can we calculate G flooring? If you remember, what you need to know for G flooring. So if we look back again to our frame, we need to know the load width of this beam. How much is the load width of beam B2? Anyone know?
2.5? Would it?
Yeah,
Would
just
it be
if we go back, so how much the spacing? 6.
off?
Yeah, we just for this example, because I don't have other number now. So for this example, if we are designing this beam B2, how much the load width will be?
6 meters.
Yeah, 6 meter, half from top, half from bottom. So this will be our load width, which is 6 meter, right?
Yeah.
So if we go back here, the load width is this value, which is 6 meter. Okay, because G flooring will be the self weight of the flooring times what? Times the load width of the beam, right? So it will be 51.5 kilogram per squared meter times what? 6 meter. Okay, so G flooring will be equal to 51 times 6, it will be 309 kilogram per meter. So this is in kilograms. So how can we convert it to kilonewton per meter?
Times it by 9.8 and divide it by 1,000.
Yes, times 9.8 and divide by 1,000. So this will be 3.03 kilonewton per meter. So this is the self weight of the flooring. Okay, I think this one is similar to the roof sheeting, but just the self weight of the flooring is a bit higher, so that's why the value is a bit higher. So what is the second component from here? Secondary beams, right? So the second component will be G secondary beams. So how much the secondary beams? Or how can we find G secondary beams? This one is similar to the purlins, right? How can we calculate the self weight of the purlin? If you remember, or how to calculate the purlin weight transfer to the beam? Do you know?
Is it the load width?
Yes. How much we need to find? The idea here is we need to find the weight of one beam, one of the secondary beams, right? And then multiply by the number of secondary beam and divided by the length of B2. So G secondary beams will be the self weight of secondary beam this weight of 1 meter of each secondary beam times the load width of the rafter, which is 6 meter. So this is the length of one of the secondary beams. Okay, just let's make it instead of number now. So this is times the load width of the rafter. Okay, times number of secondary beams. So this together is weight of one secondary beam times the number of secondary beams. So now we find the weight of all secondary beams. We should divide this by the span of B2, the span of B. Okay, so if we want to finalize this one, so G secondary beams will be equal to the self weight of secondary beam. How much we assume secondary beam? What is the size? This is the size. So how much is the weight? This part is the weight or the mass. So it will be 44.4 kilogram per meter. How much is the load width? 6 meter. Okay. How much is the beam span in this case? The beam span in this case was how much? 10. If you see here, how much is the beam span? 10. Sorry.
Yes, 10.
Yes. Okay. So the beam span is 10. Okay.
Wait, what's it?
Do you have a question?
No.
Okay.
Mhm.
So what is still what we need to know as well? How much secondary beams we have? So how much secondary beams we have?
Well, that's an assumption, right?
Yes, this depends on our assumption here. So
Yeah.
if this total is 10 meter, right? So the
Mhm.
number of secondary beams will be 10 over 1.1 meter because we assume the span as 1.1. So 10 over 1.1. So we have 9 spacing.
Mm. I assumed my span is 1.5. Is that okay, or should I change it to 1.1?
No, you can't assume it as 1.5. It doesn't matter.
Okay.
It will not change much, but I mean, just to follow what we have done here. But
Mhm.
the secondary beam can be from 1 to 2 meter or 2.5 meter. So it's up to you. Okay, so if we have here, assume the number of secondary beam will be 10 over 1.1. So we have 9 beams. We can take it as 9 beams if we assume it as 1.1. Okay. So this will be multiplied by 9 beams. Okay, so the number, the final value will be in kilogram per meter or what? So I'm just calculating it. So this value become 218 kilogram per meter. Again, what we need to do, we need to convert to what? Newton, kilonewton. How to convert to kilonewton per meter? 218.16 times 9.81 divided by 1,000. So this will be 2.14 kilonewton per meter. Okay. Do you have any problem with the second component? So we have
No.
now this one component. This is second component. What else we need to do?
The self,
Yeah,
is it self
just
weight?
as a self weight. The last one is the self weight. So G self weight will be very easy. This one. Why? Because we already assume how much the section we assumed for the rafter. This one, right? So how much is the mass? 92.4, right? So it is 92.4 kilogram per meter. So we need to multiply by 9.81 divided by 1,000 to convert it to kilonewton per meter. Okay. So this become 0.906 kilonewton per meter. So how much final did G on B2? It will be the three values together. 3 plus 2.14 plus 0.906 kilonewton per meter. All of this together will be 6.076 kilonewton per meter. So this is our final dead load on G2. Is this
Okay.
easy one?
Yeah, that makes sense. Just to see if it's okay, I've already done all of my calculations, but I did add in services weight along with it. Does that matter? Just because I've done everything else.
Is it
No
okay if we
problem, no
keep?
problem. Yeah, keep
Yeah.
it.
Okay.
Keep
Okay.
it.
Yep, that makes sense for us. I don't know if that makes sense for Shannon.
Yeah, that makes sense for me. Thanks.
No worries. If you have any question, guys, just let me know, okay? I just try to go through the calculation because I have received some question about the beam calculation, and most of the calculation is for like something similar to B1, and actually it is not like B1. Cannot be like B1 because B1 is a roof and B2 is not a roof, so it cannot be same. Okay?
Yep.
And that's why that's why it is different. Like if it is same, so why it is repeated again in part 2? Does this make sense? Okay, so now we have finished the dead load. And how about the live load? So this is our final dead load. And next will be live load. Do you have idea what is the live load on B2? The live load in B2 depend on the flooring or the floor use. What is the floor use? And if you have idea what is the floor use?
Is it like warehouse storage area?
Storage area. So do you know how much is the live load for a storage area?
Is it 5 kPa?
Yes. So I just try to open the standard for you. I just downloaded today, so can you see the screen now? Just sorry, quickly. Can you see it now?
It's still on your, oh yeah.
Yeah. So if we look at this table, so this table is table 3.1 in AS 1170.1 because you need to refer to the references you use. So this reference values for imposed floor action. So why we are looking on this table, because this is floor action, right? So it is not similar to this one here. Why it is not similar to this one here? This is not the one we are using in this part of the project. Are you with me or not?
Yep.
Yep. So it cannot be 1.8 over a plus 0.12 because this is roof. So again, we are looking at floor. So if you look at the floor, we have many values because it depends on the use of the floor. So if we look at the one quite similar to us, so yeah, if we are in warehouse, for example, and fire rooms and office storage spaces. So if we are in storage spaces, so how much is the uniform load we have? How much is the life load we have? 5.
Sorry to interrupt, but what if it's a residential shed? Would it be more likely to be general storage?
Yes, can you find it? I couldn't find it in
Yeah,
this one.
it's if you go down to where you were before, it was
Yep.
2 kind of boxes ahead up above what you were doing, which said I think it was so it's still in E, table 3.1E. Back
Here?
down where you were. No, I'm back down where we were before, just literally looking at.
Okay. Here?
Yeah, under warehousing.
Yes.
And basically the top box under specific uses says general storage. Yeah,
Yeah,
can
yeah,
that
but
be
this
used?
one, yeah, this also can be used, but because in the project details, I think it was not written clearly. It's just a storage, right?
Yeah.
I just try to make sure it is. Have you look at it soon?
Sorry.
Is it storage or general storage, or I just try to open the file to make sure what is exactly written there. Yeah, it is
it-
storage area only. So I just open to you. This is clean one. Can you see it now?
yeah.
Yep. So purpose of floor. Sorry. Yep, a storage area. So it is not clearly so anything related to storage will be accepted. You understand what I mean?
Yeah, thank you.
Yeah, because it's not clearly mentioned similar to the terms in the standard. So you see here cold storage 4.5.
Yep.
Paper storage, yeah, a lot of storage. So you can also use the general storage. I just tried to use this one because this one is clearly 5 kBA. But if you use general storage other than specified, so it will be 2.4 times the height of the story.
Yep.
Like for example, if we return back to our example here. How much is the roof height here? Sorry, this story height, how much? You need to find this area, the height of this area, which is 5 meters. So the life load on this one will be how much was 5 times 2.4 kBA. So the value will be 12 kBA.
Yeah.
Okay, so I just try to choose 5 because 5 is just simply like for example, if we said office storage. How
Have you
much?
changed your screen? Sorry, Ahmed.
Yeah, sorry.
It's in the Word document.
Sorry.
No, that's okay.
I tried to use screen, but yeah. So
Sorry.
now it is screen.
Yep.
Yeah,
Oh,
yeah.
yeah.
Okay.
Yeah.
Yeah. Sorry, guys. So now
No,
depend on the floor use. So if we consider it as office storage, so how much the life load Q will be equal to 5 kBA. If you want to use general storage areas, so it was Q equal to
I think it was like 2.5 or 2.4.
yeah 2.4. Sorry, but the software crashed. Still can see my screen, but it will crash now. Sorry, this happened. Oh, okay. So, yep, it works now. Yep. Okay. I don't have a space. Sorry.
That's
So
okay.
you can, yeah, but just need because I need to share it with the other guys. So you can send me a link or something to download it. This will be great.
Okay,
Thank
yeah.
you.
No worries.
Okay, so if we return back, the two cases will not be applicable on our example or our project, but just if you want, because both of them can be considered as a storage. So why I multiplied by 5 meter here. This was your question, Georgia, right?
Mm-hmm.
Yeah, because if we return back to the standard, what is the standard mentioning here?
Oh, that's the KPA.
Yes,
Yeah.
it is 2.4 kBA for each meter of the height. So
Mhm.
if you have 1 meter, 2.4, 2 meter, 4.8, and so on. So if you look at our example, how much is the storage height here?
5 meters.
Yes, this will be all this area will be storage height. So
Okay.
the storage height is 5.
Yeah.
So Q will not be only, sorry. Q will not only be 5 kBA, sorry, 2.4 kBA, it should be multiplied by the height. So the total that life load will be 12 instead of 2.4. Okay, but if we look at our case or the simple one, office storage, it is
Mm.
directly whatever the height, 5 kBA.
Okay.
Okay, that's why it is easier. Okay, so now we have the life load as kBA. So how much Q on B2? Because we need to find the load in B2 as kilonewton per meter, not kBA. So how much the life load on B2? Do you know? We need to multiply Q times what? The load width. Because all the loads on the beam should be in kilonewton per meter. So it will be Q, which is 5 kBA, times how much is the load width we mentioned earlier? How much is the load width here? 6 meter. Okay. Do you understand this one? So how much is the total load on the beam? 30 kilonewton per meter. Okay. All good, Shannon?
Yes, thanks. Yep.
Yep. Just because this value in kBA, so we need to multiply the kBA value times the load width to get it in kilonewton per meter. So now, what are the loads on the beam? What are the loads on the beam? G equal to what? 6.07 kilonewton per meter, and Q equal to 30 kilonewton per meter. What is the next step is, if you remember, or if you tried it already?
Manual.
Yeah, load combination first.
This.
Mm.
Have you done the load combination before?
Yeah, we have.
Yes. So how much, what is the load combinations we have?
We will have A, B, and C because D and E include wind load.
Yep. So the idea here is this an internal beam, so there is no wind loads. So the load combination we have, the first one is 1.35. This load combination for ultimate, okay? Just another before this. So we have ultimate combination or strength combination and surfaceability combination. So the ultimate combination are 1.35 G, 1.2 G plus 1.5 Q, and what else? 1 G plus 1.5 psi Q. Where I get this from? Where we get this from? We get this from AS 1170.0. Okay. Do you have any problem with this one?
No.
No.
Okay. So just try to open it to show you. Okay. So I think you can see it now. Can you see the standard? The other standard?
Yep.
If we look here, so these are our strengths combination. So we have ED equal to 1.35G, ED 1.2G and 1.5Q, and ED equal to 1.5G, sorry, 1.2G plus 1.5 Epsi LQ. So this has wind, we don't have wind. This has wind, we don't have wind. And this are for earthquakes, we don't have earthquakes. So we have 3 load combination. And how much Epsi L? Epsi L, if you go to the next table, so this Epsi L. What are our beam supporting? Floor or roof? Floor, right? So how much Epsi L?
Be 0.6.
Yes, if it's storage, so it will be 0.6. So Epsi from this table, Epsi L equal to 0.6. So if you calculate, so I have 0.35 G, we have 0.2 times 6.07 plus 1.5 times 30, and we have 1.2 times 6076 plus 1.5 times 0.6 times 30. This is the 3 values we have. Okay. So this one will be 8.2 kilonewton per meter. The next one, this one, 52.28. The third one, will be 34.28. So which one is the most critical one? So we are
52.
looking on, yeah, the second one. So this will be our load combination we need. Okay. So ED will be equal to 58.28 kilonewton per meter. So what is the next requirement is draw the bending moment diagram and shear force diagram, right? This was your question, Georgia, right?
Yes, it was.
Yep. Okay, so what is the beam we are looking at? B2. In this case, B2 is simple beam. Also in your case, simple beam. In this example, the span of this beam is 10 meter. How much the total load we have? ED equal to what? 52.28 kilonewton per meter, right? So we need to draw the shear force diagram and bending moment diagram. Okay, so we need to draw like some guidelines here. So need to make that 3 drawing like underneath each other like this. So quickly, the value of the shear will be this reaction here and this reaction here, WL over 2. So maximum shear or V max. So I can give you just directly, because this is also one of the requirement. What is the maximum shear and what is the maximum moment? What is the maximum shear formula? This is the maximum shear formula. So WL over 2. Okay, so what is W? This is W. W is the load, 52.28. So it will be 52.28 times how much L? What is L?
10.
Oh,
10.
so for us, 4.
Yeah, for you it would be depending on your group, but over what? 2. So how much is the shear, maximum shear? Will be 52.28 times 10 divided by 2. So it become 261.4 kilonewton. Okay, so the shear drawing will be the reaction you got here, WL over 2, 261.4, and the other one is 261.4 on the other side, and you connect them with a straight line. So this is the shear force diagram. Okay. Do you have any question about this? So this drawing is called shear force diagram. How much is the maximum shear? The shear at the support, 261.4. Okay. Do you have any question about this one?
No, thank you. That makes sense.
No worries. So how much is the moment? The maximum moment is WL squared over 8. So you need to just memorize this too. These are like basic rules for the maximum or the shear force and the bending moment for the simple beam with uniform load. Okay. So this all the time will be WL squared over 8. Again, what is W? W is the load, 52.28. How much L? 10, right? And over 8. So how much is the maximum moment? MMX? 52.28 times 10 squared divided by 8. So the maximum moment is 653.5 kilonewton meter. The most important thing here as well is the units. How much is the unit here? Kilonewton. So the shear should be in kilonewton. And how much is the moment? 653 kilonewton meter. So if I ask you to draw the bending moment diagram, what is the shape of the bending moment diagram? The maximum moment is in the middle here, and at the two ends it is 0, and we connect it with a curve or a parabola. This is positive moment. The value here is 653.5 kilonewton meter, and this is our bending moment diagram. Okay. So what you will do in your project, same shapes, but just the values will be different, right? Are you okay with that? Or do you want me to repeat?
Is why is down positive for the bending moment diagram?
Yes, this is just like agreement between the engineers or the person deal with that. So for the shear force diagram, if you can see above the datum is positive, below the datum is negative. For the bending moment, it is above the datum negative, below the datum is positive. Okay, there is idea about this. Maybe if you want, I can tell you why. But the idea is when you bend the beam, if you have a beam and you bend this beam, right? Which side of the beam will be like under tension? Which side of the beam under compression? The bottom side of the beam will be under tension. The top side of the beam will be compressed, so under compression. That's why to make it easier, they ask to put the positive moment or the moment on the tension side. Okay, so that's why below the datum is positive.
Okay, thank you.
No worries. Okay, do you have any question about the drawing of bending moment diagram and shear force diagram now?
No, thank you.
All right. So what is the final step? The final step is design or select the beam section. How to select the beam section? Do you know how to select the beam section? What we have now for the beam, we have M maximum on the beam. How much M maximum on the beam? 653.5 kilonewton meter. So using this moment, we need to go to the capacity tables, okay, and select UB section, right? And compare it to what we have used before earlier here. If you remember when we calculated the dead load, we have select already 563 UB. So we need to make sure that this 563 UB is sufficient for our bending moment. Okay. So have you used the capacity table? Do you know where is the capacity table? Can you see my screen now? Can you see this is week 10 content of superstructure, and this is the capacity tables. Can you see it?
Yes, we can.
Yes. So this is our capacity tables here. So if you look here, so just try to make it. Okay. So if you can see here on the vertical axis, this is the capacity moment or the capacity, the member capacity. And here is the effective length. Okay, so we already know our moment. How much our moment? 653 point something, 0.5. But we need to know how much our effective length. How much our effective length?
So we go,
Was your effective length 6? I can't remember.
Yeah, if we look at the effective length here, because the effective length will be affected with the secondary beams as well, right? Okay, so how much is the span of the beam? I will draw it here. So how much is the span of the beam? The span of B2 is 10 meter, right? Is that okay?
Yeah.
Yeah, so, but if you return back to the beam examples or the design of the beam, so this beam is under tension here. So we should look at the support L unsupported or the lateral restraint of the beam. Have you seen this before? Lateral restraint. Because the secondary beams will help the buckling, will reduce the buckling of the beam, right? Because they are on the compression side. So how much is the spacing between our secondary beam in this case? 1.1 meter. So how much L effective in this case?
It's 1.1.
1.1 meter. This is similar to the beam example, but the beam example, we have the purlins. In this example, what is replacing the purlin? What do the similar rule of the purlins? The secondary beam. Okay. Are you okay with that? So how much the values we know to go to the table? The moment 653 and L effective 1.1 meter. So if I open the capacity tables again, if we look here, so this is almost 650 something here. Okay. So I will draw a straight line. Maybe I try to draw a line. Sorry. I'm trying to draw a line. Okay, I will draw it by my hand. Sorry, guys. So this is our line. What our L effective equal to? So this is 5 meter. So each tick of this is 1. So we'll go up from 1.1 meter here. So where is the intersect here? So our our section will be between this one and this one.
So it would be 500, 530
Yes.
UB.
Yeah, so I think we would need to take the bigger one, so it will be this one. Right? Because the even though it is closer to the smaller one, but it might be unsafe if you use the
Okay,
small one. So
yeah.
you need to be conservative and choose the biggest one.
Okay.
So
yeah.
what is the section suitable for this one? 610. Okay. So for this example, using the tables, do you have any question guys up to now? Or it's just get out of here.
No,
No, all
all
good.
good, thanks.
Okay, so using the tables, use 610 UB. What was the section? And you need to show this like a screenshot of this on the calculation as well, right? So this 610 UB, 101. So this our cross section. Okay. What is the next step is? After we select the section, do you know?
Is it finding the deflection?
Yes. The next is check surfaceability. I think this is also one important step. We need to make sure that the maximum deflection on this beam is less than or equal to the limits, which is L over 300. Okay. Where this limit come from? AS 1170.0 as well. So if we look at the standard, we already opened it before. So it's 1170.0. So if you look on the tables here, yes, here, not this one, sorry. Okay, I think it should be here. Okay, here, suggested serviceability limits. Okay, so what we are doing now, floor or roof?
Floor.
Floor, right? So we have this one here, floor. So flooring, floor joist, and floor beam. So it would be something in this one, yeah, or this one here. So how much span over 300? Okay. So how much is the maximum limit we are comparing to? Span over 300. And what is the formula we are using to calculate the deflection? G plus epsilon L Q. Okay. So the limit here is L over 300 from AS 1170.1, 0, sorry. And we need to find the deflection for the load case or load combination, sorry. G plus epsilon L Q. Okay. Where this equation can be found as well here in 1170.1 as well. So do you remember when we 11.0 again, sorry. Do you remember when we talked about the strengths combination? Okay. Do you remember when we talked about strengths load combination? There is also serviceability load combination somewhere here. So this is the serviceability load combination here. So we will be looking at G plus epsilon LQ. You don't need to find it from here, but if you want, it is here as well. So the combination for serviceability is G plus epsilon L Q. Okay. So if we look here, how much was G? G was, so our E for serviceability, G was equal to, if you remember, 6.07 and Q was 30. So it will be 6.067 or 0.7, sorry, plus how much epsilon L?
0.6.
0.6, and this is 30. So because if you use the root for strength, this will be incorrect and you will lose some marks, but you should use this load combination. So how much the load is 36.67 kilonewton per meter. So this is our load for the serviceability calculation. Okay, so again, what is AS? ES equal to 36.67 kilonewton per meter. So how can we calculate the deflection? If you have a simple beam with a uniform load 36.67 kilonewton per meter, the maximum deflection, do you know where the maximum deflection will be? In the middle? Do you know the formula? Have you tried the formula? Delta max equal to what? 5 over 384 times W L to the power 4 divided by EIX. Have you seen this formula before? This
Yeah.
formula in the slides for beam design, and this is the formula to calculate the maximum deflection. What is the element or the parameter of this formula? 5 and 384 are constants. What is W? W is the UDL. What is L? The beam span. What is E? E is the modulus of elasticity of steel. Are we using any other material in this course for beams? The material of this course will be steel all the time for this course. So it is 2. It is constant for the material. So it is 2 times 10 to the power 5 MPa. Okay. And what is I? Ix is the inertia of the section. What is the cross section we use now? 610 UB 101. Okay, do you have any problem with the elements? Just like interpreting the elements, and now we will know how to calculate it. This is span L, and this problem is 10 meter. Okay, so if we want to calculate what we know and what we don't know now, what is W? How much is W? Do you know?
Is that the 36.67?
Yes, this is the load W. And how much L?
L will be 10.
10 meter. How much A? What is the last element we need to know? I. How can we find I? From the tables for UB section. So if you open the course website again under week 10, you see this top one, read universal beam and universal column properties. So from this file, you can find the section properties. What is the section we are using now? 610 UB 101, right? So if you go straight like this, which one is I? This is I, right? Can you see it? Maybe I make it bigger. Can you see it now? So how much I for this section? 761 times 10 to the power 6. Don't forget, because the column head is multiplied by 10 to the power 6. So if we return back to our example here, Ix equal to 761 times 10 to the power 6 millimeter to the power 4. Okay, do you have any problem with extracting I from the tables? All good?
Yep, all good.
Okay, so now how much delta max if we substitute? So we have 5 times W. How much W? 36.67, but this is in kilonewton per meter. Times what? L to the power 4. How much L? 10 to the power 4. Divided by 384 times E 2 times 10 to the power 5 MBA. I just draw like write down the numbers with the units we have now, but this not are the correct units, okay? Just to let you know that we need to do some unit conversion before. So how much I? 761 times 10 to the power 6. Okay. How much, what is the unit of this in meter? This in millimeter to the power 4. If we look at the units are consistent or not consistent? For example, here, kilonewton and meter. Here, meter. But here in millimeter. Here, megapascal. How much megapascal equal, or what is the equivalent unit to megapascal? Newton per millimeter square. So now we have some unit in Newton, some unit in kilonewton, some unit in meter, some unit in millimeter. So this is not correct. So we need to make the unit consistent. How we make the unit consistent? Convert all to Newton and millimeter. So if I ask you, if we have 36.67 kilonewton per meter, how we convert it to Newton by millimeter? Do you know? To convert kilonewton per meter, to convert from kilonewton to Newton, we need to multiply by 1000. From meter to millimeter, we need to multiply also by 1000. Okay? But here, meter in the denominator. So the 1000 will go with the 1000, so it will be same value. So just to don't waste much time, the value in kilonewton meter is equal to the value in Newton by millimeter. Okay? Are you okay with this one? So this one is same in Newton millimeter. But how about the 10 meter? How we convert 10 meter to millimeter? Do you know?
Times it by
1000?
1,000 again.
Yes, times by 1000. So this will be, this is okay now. So this become now in millimeter. So all the numerator is in millimeter now. So do we need to convert anything else? So now all the units are Newton, millimeter, Newton and millimeter. So now all the unit is okay. So what you need only to keep in mind to convert the span L from meter to millimeter. Are you okay with that? So if you calculate sigma max now, if we calculate this one, okay, sorry, just there is a problem. 5 times 36.67 times 10,000 to the power 4 divided by 384 divided by 25 divided by 161 6. So the final deflection is 31.37 millimeter. So the final value of deflection in what is the unit of it? Meter or millimeter? Millimeter. Can it be meter? Is it logic to be deflection in meter, like 31 meters? This means that the beam will be like to reach the ground or under the ground. So 31 meter is not a logic number. Anyway, so what is the next step after we find the maximum deflection?
Sorry to interrupt. I got my answer as 1 millimeter. Would that be way off?
Yes, I think so. Because what is the load you got? It depends also on the span, because what makes the deflection very big here is the span is 10 meter. If your span is like 3
Mm.
meter, 2 meters, so it will be less, much
Yeah.
less.
My span was 4.5.
2.5.
Yeah,
Cool.
4.5.
Yeah, just try to revise the calculation, and if it is like still the same, so no problem. But I
Okay.
mean here, because we have a big value of load as well.
Mm-hmm.
So well, how much is your load?
My load was 20.79.
Yes. So I can calculate it for you. So 20.79.
Yeah.
What is the span?
The span was 4.5.
4.5. So 4,500. How much your section? Like how much I?
We recognized that we needed to change that, so I haven't figured out the thing for it yet, but our beam is 310 UB 32.1. I need to get the
Yep,
Thank
310 UB.
UB 32.0, sorry.
Yep, so 63.2. 6. The deflection should be 8.78 millimeter.
Oh. Okay, thank you.
No worries. Based on the number you mentioned. So
Mhm.
anyway, so do you have any question up to now? You can update, no problem. So still have time. Okay, what is the next step is after we got the deflection? We need to compare sigma max with what? With the limit L over 300. How much L again?
It's
10
10.
meter. Yes. So delta max already, we know it as 31.33 millimeter. L over 300, which is 10 over 300. Why I add these 3 zeros? Because it's 10 meter, right? We need the deflection limit to be in millimeters, so we need to multiply by 1,000. So the limit will be 33.33 millimeter. So if we compare both together, which one is bigger? Or delta max equal to 31.37, more or less than L over 300 equal to 33.33 millimeters. So this section is adequate or not adequate for self-stability or for deflection?
Adequate.
Yes, it is below the limit, so the section 610 UB 101 is adequate, right? So this is the steps of the beam design from A to Z. I think that's all. So do you have any question about the beam?
No.
No, I don't.
Okay, all good now. So if we continue, what is the next step will be the beam design. So for the beam, the column design. For the column design, because this example is already for column, so I will just go through what is there, okay? So if we look at the column, what does this red area mean or indicate? This red area, sorry, the black area now, this is called the tributary area of column. Okay? What is the dimension of this tributary area? How much is this one in this direction? 6 meter. And in this direction, how much? Like this all 20. So half from left, half from right, so it would be 10 meter. So if I ask you, what is the tributary area for this column C3 or C2, whatever the name? How much is the area? 10 times 6, so it is 60 meters square. Okay, do you have any problem with that? Because this, if this is not correct, so all the column calculation will be wrong. So you need to make sure this value is correct. So tributary area, 6 meter times 10 meter equal to 60 meters squared. Okay. So if I ask you to calculate the dead load and live load on the column, so how can we calculate dead load and live load on the column? I will leave you to respond because we already have done the beam. So the column will be quite similar, just a few changes. So if I ask you, what is the dead load component on the column C3 here?
I've put down services, self-weight, flooring, secondary beam, and main beam.
Okay, so G column will be G flooring and G secondary beams and G rafter and G self weight. Okay, because you have surfaces, you add one more component. So how many components we have here? 4. They are same component. This one is only added because we have to include the self weight of the column itself. So if I ask you, what is the self weight? What is the flooring self weight, G flooring? How can we find G flooring in this case? G flooring will be the self weight of the flooring times what?
The tributary area.
Yeah, so all the load weights and beam calculation will be replaced by what in the column? Tributary area. Okay. So how much is self weight? It was 51.5 kilogram per square meter. How much is the tributary area? 60 millimeter squared, right? So how much this value is? 3090 kilogram or what? Or kilonewton or kilogram per meter? Which one? Nazia has left, or she doesn't want to respond.
Oh no, I'm here. I'm sorry. I'm following along.
Okay, so is the kilograms correct or no?
Yeah.
Is it
So we have
kilogram meters squared?
no kilogram per square meter multiplied by meter square. What happened meter with meter? So what is left?
No,
Kilogram.
just kilogram.
But we need to convert it to kilonewton. So any load on the column, this also you need to keep this in mind, should be in kilonewton, not in kilonewton per meter. So what is the difference between beam and column in terms of units of loads? In beams, kilonewton per meter, in columns, kilonewton only, right? So how will we convert 3090 kilogram to kilonewton? We multiply by 9.81, sorry, divided by 1000. So this become 30.31 kilonewton. Okay. So are you okay with that?
Yes.
Okay. So this is just an example. So if we look at the remaining, so what you can see here, this is the load of secondary beam. How much is G secondary beam? G secondary beam, we will calculate the load of one beam and multiply by the number of beam. So it is similar to what we have done before, but here it will be in kilonewton. So if we continue here, just to show you this one again. So for G secondary beams, what will be the calculation? It will be G self weight of beam, right? Of secondary beam times what, if you remember?
The number of beams.
Yes, the number of beams. Time also the load width of beam, because this is the length of the secondary beam, so, right? So times the load width of the beam times what? The number of secondary beam. Okay. So why I didn't divide by the length of the beam? In the calculation of the beam, we divide by the length of the beam. Here, we will not divide by the length of the beam because we need to find the load as kilonewton. Okay. So to find the load as kilonewton, we multiply G self weight. So this in kilogram or kilonewton per meter times the length of the beam. This is meter. So kilogram per meter times meter. So we get the value in kilogram. So this is the value of the load of the beam in kilogram. So if we multiply by the number of the beam, so this is the total beam load. Okay. So how much the secondary beam in this case? In this case, it will be G self weight 40.4 kilogram per meter times load width of the beam was 6 meter. The number of beams was 9 beams. So this value become 40.4 times 6 times 9 become 2181.6 kilogram. So this value is in kilogram. So we need to convert it to kilonewton. So G secondary beam, how we convert it to kilonewton? Times 9.81 divided by 1,000. So this become 21.401 kilonewton. So this is the load of secondary beam. This was the load of the flooring. So we have flooring, secondary beam. How we find the load of the rafter? How we find the load on the of the rafter? So what is the rafter self weight? So this is our rafter. Sorry. So this is our rafter. So we need to know how much of the rafter inside the tributary area. So how much of the rafter inside the tributary area? 10 meter, which is the width in this direction, right? Is it logic?
Yeah.
Because this column will carry only 10 meter of the rafter. What about these two parts? This part will go to this column. This part will go to this column. Okay. So G self weight of rafter or G rafter self weight of rafter will be how much? Will be 92.4 kilogram per meter, which is the self weight of rafter. Multiplied by what? By 10 meter. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the rafter within the tributary area. 10 meter is the length of the r Okay, so again, this kilogram per meter times the meter. So the value will be in kilograms. So G self weight. And which beam we need to use now in this example? Because we have changed the value, right? Because in your project, you are continuing the column after the beam, right? So which beam you should use? Is this correct, or we need to update this one? Is this value correct? Like, because in your example, in your project, you may need to change the rafter. So what is the final rafter we used? 610 UB. So if you update your rafter, so what you need to do here? You need to calculate the on weight of the rafter based on the new beam. Is that logic? So I will just update it here. So 101 times 10, this become 1010 kilogram. So G rafter will be 1010 times 9.81 divided by 1000. So this become 9.908 kilonewton. So as you can see, all the loads should be in kilonewton. What is the final part or final portion of the dead load on the column? The self weight of the column. How can we find the self weight of the column? Do you know? What we need to do to find the self weight of the column? We need to assume the column cross section. What is the column cross section should be? UC or UB? UC or universal column. So we will use this one here, similar to this example, 200 UC 59.5. How much is the on weight of this one? Do you know?
59.5.
Yeah, no, 59.5. But this 59.5 on weight of column equal to 59.5. This kilogram per meter. This mass is for the per 1 meter of the column. So per meter. So do we accept this one per meter, or we need to convert it to kilonewton kilograms? So if this our column, how much is the height of the column here? 5 meter. So we need to find the total weight of 5-meter column. Each meter of this column equal to what? 59.5 kilogram per meter. So how much is the total self weight or the self weight of column? How much is self weight? If 1 meter is 59.5, so how much is the 5 meter? So it will be 59.5 kilogram per meter times the column height, which is 5 meter. So this value will be 297.5 kilogram. Again, we need to convert it to what? Kilonewton. How we convert it to Newton? Kilonewton. 9.8 divided by 1000. So this become 2.918 kilonewton. So do you understand that? Do you have any problem with the load?
No, that's all good.
Okay, thank you. So how much is the total dead load on the column? It will be summation of all the components we got. So from here, 30.31, right? Plus what? 21.401, like the secondary beams, plus the self weight of the rafter, 9.908. What is the final component we have? The self weight of the column, 2.918. So the total would be 33.1 plus 21.401 plus 9.908 plus 2.918. The final value is 64.537. What is the unit for this load? This is one important thing. What is the load? What is, sorry, the unit? Do you know? So what is the unit here? Kilonewton. So what is the final unit? Kilonewton. So G for the column is kilonewton. What is the next step for the column? Are you tired? So
No, it's the live loads.
yes, if you want to finish now and you continue later, it's okay.
Oh no, we're all good.
All good? Okay. So this for the dead load. What is the next step? Live load. So what is the live load again?
It will be 5, or if you did the other one, was it one?
Yes, but it will be 5, but not maybe, it must be 5. Why it must be 5? Because what we have done in the beam, are the beam and column carrying different floor or same floor?
Same floor.
So the live load cannot be changed, right?
Yeah, yeah,
Yeah, so whatever you have used in
yeah. So for your
whatever, yeah,
V5.
yeah, because some cases like they are, if you use different, this means that you don't understand that beam B2 and C1 are not carrying the same floor, right?
Yeah.
Yeah, so the next is the live load. So how much Q? Sorry. Q on the column. Q on the column will be 5 kBA times what?
Is it 60?
60 meter square. kBA equivalent to kilonewton per square meter. So Q column will be 300. What is the unit?
Kilonewton.
Kilonewton. Yeah, so all the load on the column should be in what? Kilonewton.
Yes.
Again, what? No internal wind here.
Mm-hmm. Yep.
Okay, what is the next step? Load combination. So we don't have this two because we don't have what?
We don't have
Wind.
wind load.
Yes. So they are same 3 load combination. So this is, I just will replace these values with the values you already got. So how much was our, it was close, so 64 point something, so it will not that much difference. So 1.35 G, 1.2 G plus 1.5 Q, 1.5 G, sorry, 1.2 G plus 1.5 Epsi L, Epsi L 0.6, 300. So what is the maximum load?
564.7.
Yeah, 564. So N, because we are looking for N max on the column equal to what? 564.7 kilonewton. So this is the value we are looking at to design the column C2 or C1 in your project. So this will be similar to what you will be doing in the project. What is the next step, Shannon? You mentioned this was your problem, right?
Yes.
Yes. The next is L buckling in plane and L buckling out of plane, right? Why we need both of them? We need both of them to go to the chart. So if you look at the chart, we have 2 charts. One chart for L buckling in plane or in about x-axis. Can you see this chart? So this L buckling in plane. And this chart is L buckling out of plane. So you need to find 2 values of L buckling. So L buckling X or L buckling in plane. This will be K E times L. L buckling Y or L buckling out of plane. How much will be L buckling out of plane? It will be all the time L. So L buckling X in plane will be KEL and L buckling out of plane will be L. Have you attended the last tutorial? I think I saw Georgia last week, but I don't know if Nazia or Shannon have attended.
No, I couldn't make it. Sorry.
No problem. I just ask if you, because this was explained in last week class, so that's why I'm asking. Okay, so we have these two buckling lenses. We need these two buckling lenses to go to the charts and to find the section, the cross section needed. So if you look at here, so again, L buckling in plane is called LBX. So this in plane buckling. L the EY, this L buckling out of plane. So what is the formula for L buckling in plane and out of plane? For L buckling in plane or about x-axis, it is K effective times L. And for L buckling out of plane, it is L. What is L in both the column height? So how much is the column height in this example? 5 meters. So what we need only to know now, how much KE, okay? KE in the last tutorial, we have done some calculation using the charts, but the standard have give us some simple values. So if you can see this table, this is the values of K effective. Depend on the two ends of the column. So we can have the column fixed, or hinged, fixed, or hinged, or hinged, fixed free. So in this example, so okay, again, depend on what is the two ends of the column. Do you know this support? Have you seen this support before? What is this support is? Fixed. And this one is hinged. And this one is hinged or pin. So K effective depend on that. So for example, here is 1. If you look at the table, here K is 1 for pin. Here K is 0.7 or 0.85, sorry. And here is 0.7. Okay. So I think you don't need to go in depth with this one, but just in our project, because the project, our column is, what is the column in your case? Can you open the case? I think it doesn't change from last year, so it will be fixed at the bottom, and we consider it as free at the top. So it is fixed and free. How much K effective for this case? 2.2. Okay, so how much K effective now in this case? 2.2. So how much LEX? How much LEX? LEX or LBX or L buckling in plane will be KE times L. K equal to 2.2 times L, which is 5. So the value will be 11 meter. L buckling Y or L buckling about Y or L buckling out of plane, all these names are okay. Equal to what directly? L or KAL? L. So how much L? 5. So how much is the buckling length for our example here? 11 and what? 5. So L buckling Y 5, L buckling X 11. Okay. Which case we got this from? This is the case. because our frame it will be subjected to sway, so this is the value of KE. Okay, in your project it will be also same value, 2.2. Okay, do you have any question about that now?
No, we're all good.
No, thanks. That's good.
No worries. So what is the next step after we find the buckling LX, LEX and LEY? We will go to the charts two charts with N and LBX in one table and select section. And we will go to the table, another table with LBY, N with LBY, and select another section. And from these two sections, we will choose the bigger section. Okay, so if you look here, how much was N? N was 565. So this is the value, and we enter the chart with this value. How much L buckling in plan? 11 meters. So at 11, we go up with a line. So where these two values intersect, somewhere here. So which section is close to it? This is our section. So what is our section? This one. So from this one, use 200 UC 52.2. Is that correct? Okay. So this using L buckling implant. So the next step is using L buckling out of plan. How much L buckling out of plan was? 5 meter. So LBY was 5 meter here, and we go up with a straight line. How much was N? N was 565 kilonewton, so somewhere here, and we go with a straight line. Okay, so this is the point. Which section is the closest one to it? This one. Okay, so why he chose the red one? So from this chart, we need to use U200 UC 46.2, right? So just need to. Are you still with me, guys?
Yep.
Yeah.
Yep. So LBX and N, we will use 200 UC 52.2. For LBY and N, we will use 200 UC 46.2. So which section to use for the column? The biggest one. Which one is bigger? 52.2. Okay. So what is the section will be used for the column? 200 UC 52.2. Are you okay with that?
Yes, yep, that makes sense.
Yes. So that's why he just pointed to the red one directly, because the red one is bigger than the green one. So we need to choose the bigger one. Okay. Are you okay with that? So this is the final step in the column design. So
Yeah, we're all good with that.
We just had a question if we just want to confirm that Shannon's okay with that.
Oh yeah,
Are you-
sorry, yeah, I'm all good.
Okay, we just had a question, sorry, Ahmed. It's about I think it was around bending moment.
yes, what was the
Um,
question?
If you just scroll up to your calculations in regards to the bending moment, where we were designing we were using the design capacity graph for the beam.
What was the moment around?
This one?
Yes, this one. So, second, I'm just
This
trying
one.
to catch back up to that. Yeah, so the M max, the bending moment. You've used 10 because
Yeah,
that's the span.
that's the length of the beam,
That's the length of the beam.
but our length of our beam is 4.5.
Yes. Wait, so then
Yeah, you need to use your
what was
L.
the
Oh.
span being used then?
Wait,
Sorry?
sorry, I thought the span of the beam was supposed to be what would you did 1.1 for the spacing of your
Where was that used? Yep,
that
that
one
one,
there,
that slide.
yeah.
Yep, that's the slide. You were just hovering over it
I think it
before.
might be down a bit.
Slide 11. That
Yeah.
one, yep.
Okay. Why I use L effective as 1.1?
No, we understand it was the spacing between your
Yeah.
but
Why not the beam span, right? Is this
well,
what you want?
we originally calculated ours using the span of the beam, but when we recalculated it using the spacing, we got a number that was significantly lower, and I don't think that we'd be able to use it on the capacity table. The number that we got, I think it was like 12 kilonewtons per meter. And if we try to find the universal beam from that on the capacity table, I don't think we could use 12 because the number's too low. So
I
I just
think maybe something is wrong in your calculation. But
could you go
just have a
back?
look here.
Mm.
Just
Oh,
have a
yeah.
look on this example. Have you
Yeah.
seen this example before?
Yeah.
Okay. Have you understand what is written here? So
Uh,
if the load is downward, so the top flange of the I-beam will be under compression.
mhm.
So the problem in the steel is the compression, because the compression will cause to buckling. Okay.
Yeah.
So they are worried about buckling. So when we add the purlin or the secondary beam in the example I have solved, so this beams or this purlins like work as a lateral restraint for the rafter. So the rafter become strained, and the unrestrained length or the L effective length for the beam becomes the distance or the spacing between the beams or the purlins.
Mhm.
So if you look here, the span of the purlin of the beam, sorry, how much was the span of the beam he designed? 16. But
Mhm.
what was the maximum unrestrained length for this beam?
1.85.
Why it is 1.85? Because the spacing
the
between the
escape.
purlins is 1.85.
Mhm.
So this bracing or this purlin doesn't change the moment. It just change what is the value of L effective you use in the table.
Oh, okay. That
Alright.
makes a lot more sense.
So we
Yeah,
will
so yeah, you just mix up what is the moment still times 10.
Okay, that
okay.
makes
Yeah.
sense.
But when I go to the table, the capacity table, where is the capacity table? Here?
You use the spacing
Yeah.
instead of that.
Yes. And instead of using 10, I used what?
You
Like
use
1.1.
1.1.
Yeah.
Look, if I use 10 here, you see, it
Yeah.
will be, there is no section will be enough
Yeah.
to support it.
That's correct, yeah.
Yep. But
Okay.
don't mix up 1.1. 1.1 is not the beam span. It is just the L effective of the beam because of the purlins or the secondary beam we have used.
Okay, that makes sense. Thank you very much.
No worries. All good now?
All good now. Thank you.
No worries. Sorry for
No,
long. Yeah.
it's my fault. I got confused with the numbers.
No, I mean sorry because of the session was long. Sorry.
Oh no,
Oh,
we
no.
appreciate it. Thank
Yeah,
you so
thank you
much
for your
for
help.
taking
No
time
worries,
out
thank
today.
No worries, thank you. Do you have any other question? I will maybe record another video for space gas because I also have received some queries about space gas, but maybe in a different video. I will record it and send the link to you.
Okay,
Yeah, for
thank
sure.
you so much.
No
Yeah,
worries.
thank you. That'll be good.
All good, Shannon?
Yep, all good. Thank you. Thank you so much.
No, I will send you this file as well if you need it, so I can send it
Yes,
to you as well.
please.
Yeah,
Cool, thank you. And
no worries. I just need if you can like upload the video somewhere and
Mm.
I will download it. This would be appreciated. Thank you.
Yeah, we'll do that. No worries.
Thank you.
Thank you.
Thank you.
and
Go
sorry,
ahead,
quickly.
Shannon. Yeah, go ahead.
Um, sorry, you said that you'll do a Space Gas video and send it to us as well.
Yes, but maybe
Cool, thank you.
maybe tomorrow. Maybe tomorrow.
Yeah, no worries, that's all good.
Okay. No worries.
And for our presentation, do we need to present the whole report, or is it like okay if we have
No,
like
no, up
the
to
last little
what,
bit missing?
yeah, up to what you have completed, because the due date of the report is maybe after 5 days, and outside will extend it. So
Right, okay.
yeah, you don't have to.
Yeah.
Yeah, but you can put as much as you can. And actually, this presentation is just to give you some hints or feedback to improve your final report.
All right, great. Thank you very much.
No worries. Thank you. We're good now?
Yes, thanks.
Okay.
Thank you.
Thank
Good
you,
night.
guys. Have a good night. You too. Thank you.
Thank you.